Happy St. Patrick's Day, everybody, and welcome. Whether you've joined us before or this is your first time coming to one of our presentations, just want to thank you all for joining us today, taking time out of your busy day to take in this particular presentation. My name's Scott Bootler. I'm the Academy instructor out here in Langley, British Columbia. This is Viessmann's West Coast office. And joining me today, taking some time out of his day from dyeing his beer green, is Academy instructor Mark Norris. He's coming to us from our Waterloo office. That's our North American headquarters. How are you doing this morning or this afternoon, Mark?
Good, Scott. How about you?
I'm doing okay. I'm doing all right.
Not sure that I'm into the green beer though.
I was just wondering if you had what's the market for green food dye out there in Waterloo?
It's pretty big. We got a big Irish community here, but I'm not one of them. So actually, somebody was giving me heck today because I didn't have anything green on. So I said, well, I didn't realize it was St. Patrick's Day till I got to work.
Well, I can't think of anything better, like a better way to actually make green beer look appetizing than to review some wiring schematics like we're going to do today. So
there you go. Yeah. Good segue. I like that. Good afternoon, guys, or morning, wherever you are. You will find in your toolbar in your screen a Q&A box. That's for asking questions. Don't use the chat box to ask questions because we don't get all the history in the chat box, but we get all the history in the Q&A box. And what will happen is I will try to keep up with Scott in real time to answer questions that come in. If we have to hold some to the end, we'll do that. And Scott will try to address those at the end. But what will happen with the Q&A is every question that's recorded and the answers that we supply, that will be sent to you in a PDF document at the end of the webinar in a couple of days. So you'll have a copy of those, as well as a PDF version of the presentation. And as always, this is being recorded. So the recorded video will also be available on the YouTube channel, the Viessmann North America YouTube channel. It takes me a few days to do that. So just be ready to see that again if you want to watch it again. And with all that hardware and the housekeeping out of hand, I'm going to hand it back to you, Scott.
Right on, Mark. Thanks. So like I say, we're going to be looking at some schematics today. So the title of today's, and it's just part of our technical training series that we're going to load up, as Mark had mentioned, onto our YouTube channel. We're going to look at some commercial controls, the connections and the circuits. So the idea here was, we've got the manuals, and the idea with these technical training series webinars is to give you something that will complement what you're looking at in the manuals to kind of help you out. I know a lot of people like wiring schematics, for instance, they kind of relate that to similar to like staring at the sun. You stare too long at a schematic, like staring at the sun, you might affect your eyes a little bit. You might damage your eyesight. But the whole idea here is like whether you're installing this control, whether you're going to be troubleshooting a commercial control, or whether you're a guy that's operating that control, it's just important to kind of understand what you're standing in front of. A little bit of that knowledge is power as far as that goes. And it's just important basically to know once you turn that power button on these controls, like where's the power moving through there? So what we're going to try to do here today, I've got 4 commercial controls. These are the kind of the most popular current controls we're looking at. Just for the amount of time we have, we had to kind of water it down to just a few controls here, but they take up a bulk of our products that you would actually see in boiler rooms out there, or projects that you're actually currently installing or bidding on, what have you. These controls are certainly going to be part of a lot of those projects. And it's just, again, like a complement to what we already have out there available to you. Just puts it into a bit more of a visual and audible presentation format for you. So we're just going to get right into it here. And the first control we're going to have a look at is probably, I would think it's probably the most popular as far as the cascade controls that we are dealing with. So cascade controls, we've done a multitude of presentations already back in 2020. Mark did a couple, I did one. Our counterparts down in the US have done some interesting information sessions on these controls. So just kind of a continuation of that, more on the wiring side. So this control you would see in a lot of boiler rooms, whether it's the left or the right side schematic, you're looking at the bottom here. So wall mounted Vitodens 200 boilers, will cascade with an MW2C that you see in front of you here. So that would be part of that boiler room. It would be an accessory, so it's not going to be on the boiler itself. The boilers have their own individual controls. This would be basically the system controller, as well as the staging of the boilers in operation. We could do up to 8 Vitodens 200s on these units. Or on the right side here, bottom of the screen, those are the Vitocrossal 300 CU3A. So this is typically the cascade control. You might see it in some other applications too. This is primarily the function of it would be for the Vitodens 200 as well as the Vitocrossal 300 CU3A control. So there's the what you see on the control there. Obviously, is the display information that's on the display. We went through that, I think, a couple of weeks ago on some commercial control presentations about what those displays mean. You've got your power buttons. You got some fuses there. You might not see the fuse, but you'll know where it is in a moment. And of course, you've got another switch on the left-hand side we're going to talk about as well, and some LEDs. So all that make up the control. It's basically what we don't see that we're going to try to review today once when we get into it here a little bit. First thing to talk about though with these controls is there's usually 2 parts to them, and I just want to identify that because the 2 parts are usually can sometimes be in different locations. So when you have an MW2C control, one we see in front of us here, this is the wiring schematic that comes with it. A great document actually for guys that have to wire these controls up. It tells you every specific area where you want to wire your pumps or mixing valves or sensors, etc. But just so you understand, the control is going to come with a DIN rail, which is installed directly below the MW2C. It's a little metal enclosure there. All of the line voltage connections will go into the field connections are going to be wired into that DIN rail. And the factory we've taken from the DIN rail and we've plugged into the control. So we're going to try to basically kind of have a look at how the power comes in and all the outputs of that as we move through here. But just so you understand that the control is basically two parts. So you've got the actual control proper, and then you have that metal enclosure and the DIN rail, and those connections were made in the factory. And of course, all the line voltage is going to be coming into the DIN rail down here for pumps and safeties, whatever mixing valves that we have down in this area. When you're wiring the low voltage connection, so basically what we're looking at here would be like communication connections, whether that's from Viessmann device to Viessmann device, or boiler to boiler to cascade perhaps, or some other different sensors, room temperature sensors and stuff like that would be connected here, as well as any of your sensor inputs like outdoor sensors, domestic hot water sensors, those types of things, supply temperature sensors for heating circuits. Those are connected directly to the control, as well as some other digital inputs that we have on these controls we're going to review as well. So it's 2 parts. You've got the line voltage goes to the DIN rail, low voltage will terminate on the right on the control proper here, and we'll have a pretty good in-depth look at how those connections are made. So you can see we can look under the hood of the MW2C literally. You can flip the front cover up there, and you can actually hold that cover in place so it kind of stands up while you're doing all your field wiring, for instance, or you're any troubleshooting, or you just want to have a look inside the control. You could do that. Now your hands free and you can kind of move around the control without having to hold the lid up while you're looking at it. And this is what the control looks like inside. So we flip it up, and it's got another plastic enclosure. Let's remove that enclosure and have a look at the inside. And you can see that there's some printed circuit boards here. These are modern day controls. So modern day controls, you're going to see PCBs in here, these little circuit boards. And you can identify probably 5 fairly easily. We got this guy over here, another one in the middle, one over on the right-hand side. We got a couple boards up here as well. We're going to have a look at what all these do. There's actually about 6 boards on this control right now that we're going to review. And see what their functions are and how they work, and also how to do a little bit of troubleshooting, where the power gets interrupted, et cetera, and how to, what that might basically suggest the issue might be with the control. So this schematic is actually part of the manual, and most of the documents you'll see that are basically just black and white are just cut and pasted from the manual here. And those are those boards we just looked at. So we'll have a little review here. So the legend is on the left-hand side as we move through here. The first one is the electrical interfaces. All those are the plug-in connections. So these X4 plugs connecting the boards together, A1 and A2. A2 and A3 are connected with these connections here, X24, X8, as well as X8 and X7. You got a couple of other X connections here. So those are just the connections between the different boards. And the purpose of those connections would be essentially power. So they're going to steal some power from board to board here. As well as communication. So sometimes there's some communication that's going to happen between the boards when certain events happen, and these little X connections are where all that action is going to happen. So just going from, A1 all the way up to A13 here. The first one is the extension printed circuit board for heating circuits. So basically our mixing valve extension board is on the far left side of your control. You're looking at it. If I take the cover off that, we see we've got some outputs here in the white. These are all 120 volt outputs. We see a connection input here. We'll review that. We've got some sensor connections here. We have relays. So we're going to talk about all these things, how they work and where they go as we move through it. Now we've got another board here, the printed circuit board, low voltage. So this is our low voltage motherboard. So let's pull the cover off of that one. And it actually has, it's a fairly busy circuit board as other boards get plugged into this low voltage board and for communication and different types of functionality. And we'll review all those boards as we move through here. Some of the boards that we are going to look at as we move through here are actually plugged into this, and I'll try to identify those as we move through. So that's our low voltage board. You see your sensor inputs down the bottom here and some digital inputs on the right-hand side and with the gray plugs, communication in the pink. And on the far right, we have our PCB 120 volts. So there's our 120 volt motherboard. And this is where the power comes into the control, as we're going to start to look at here in a moment. More relays, as you can see, as you take the cover off, you see the little white relays here. And of course, we've got some more line voltage outputs down at the bottom of this control for us to have a look at. And of course, the connections between the low line voltage and the low voltage boards here. We've got an OptiLink and another switch up at the top here, which we call the emission test switch or override switch in some cases. Interchange those words based on the control. As well as the OptiLink here is essentially the board that has the LEDs on it, your green LED and your red LEDs. We'll talk about those in a moment and their connections. So there's the boards that we're dealing with. So there's the override switch, there's the OptiLink, and then this little board here is the connection for the programming unit. Our software card here, so we call it a PCB A8. This is actually the software card. It's plugged into the board right here. So that is actually it plugged in horizontally on our low voltage control board. Our LAN communication module, so our communication accessory here. This is sometimes part of the control when you buy it off the shelf. Sometimes it's an accessory. It depends on the control that you're purchasing, whether that board is going to come with it or not. And that's basically the LAN board. It's plugged into low voltage control board vertically and has little RJ45 connections on the bottom here. In behind this little ventilated plastic shroud is the power supply unit. So basically this it takes power from the motherboard and powers up the low voltage control board here. We're going to have a look at that. It plugs into these two boards at the top. You see the one side here, the other side over here. That's what it looks like in its entirety. And we've got a programming unit, just an on-off switch basically. So on-off, and our fuse holder is in this little control box, which is usually basically looks like it's part of the actual line voltage motherboard here, but it's connected with a little X1 plug over here on the top right-hand side of that 120 volt motherboard. That's the back side there, so we can see the connection. So for testing purposes, to getting your meter out, checking for continuity or checking for power, where it's going, you can always open that up and have a look at the disconnects here on the other side of that board. And then finally, last but not least, where it's plugged into on our control right here is, of course, the display unit itself, which is its own little, usually 5x7 type of board that plugs into the cascade itself. So there's the MWT2C control, what it looks like. Now the motherboard that we were dealing with, this is like I say, where all the power comes into, and you're going to see this. We're going to go through 3 other controls. There's going to be a lot of similarities to how this happens. So we're going to go through some fairly good detail here, and then probably a little less detail as we move through. And if you need a review, just kind of back up when the video is available, and you can have a review of what we're dealing with here. So the motherboard, 120 volt, it's connected to our power connection and of course the power supply. And it is also connected to, this is where we start connecting to the DIN rail down below here as well on the MWC. So I thought I would pull that into the presentation as well so we can see how that power moves through there. So the power comes in on the right-hand side of the DIN rail. So it's coming in on the 11 on your DIN rail. So there's in red, we've got the L coming in. And I've already detailed the neutrals. So you see how they're all tied off and the grounds, all tied off on your 120 volt circuit board here. But as the power moves up through the control, it's going to come up onto that little plug here, the X1.2. So it's coming in on that. And then it hits our switch. So first thing it's going to hit is the switch here, which means that if we switch this power off, just remember on your DIN rail, you still have 120 volt power on that 40 plug. So messing around with power here doesn't mean that you're just because you switch the power off here, you got no power at the 40. So this is before the actual switch. We got 120 volt here to kill the actual main disconnect to kill the power to the control. But this will power down the control for servicing and troubleshooting, whatever you need to do. So we flip that around, you'll see that you've got your connections here just in series. So you can, if you have an issue with the switch there, you can always test it. But as we turn the switch on, it goes directly in series with the fuse. We've got a 6.3 amp fuse. So now anything after this is now protected by the 6.3 amp fuse. So if there's anything that overloads, we're going to pop the fuse here on the board. That little fuse is sitting right in a fuse holder here. Little flathead screwdriver, little spring retention clip that you push that in and turn it counterclockwise or anti-clockwise, whatever you prefer. And you can pop that fuse out and you can just check for continuity, whatever you need to do. As it moves through the fuse, if it's good, you got power that stops at a branch here now, and it goes in 2 different directions. The first direction is it goes over to our X7 connection where our power adapter is plugged in. So our power board, which is going to deliver the low voltage power over to the low voltage board when it gets plugged into that. And of course, the neutral comes down and ties down to our bank of neutrals on the control. And then of course, we've got our power coming down here. And it comes down to the 156 connection, which is going to be plugged over. This connection here actually plugs over to the mixing valve module we're going to have a look at here a little bit later on as we move through the different boards. So that's how we get power over to that mixing valve control, is through this little 156 connection. It's essentially, you'll see 156 in a lot of our controls. 156 usually indicates that that is essentially a auxiliary power connection. So there's a power there. Always remember though, 156s are protected by an internal fuse on the control, which means that there's other loads connected to that as well. So if you overload this 156, of course, we have potential of popping this 6.3 amp fuse. So this is where I'm talking about. So that 120 volt also powers over here on a parallel connection to these different connections on the motherboard. And those are all related to these little switching relays. So these little 24 volt switching relays, you can see the 24 volt is right here, and they're a 24 volt DC relay connection. And essentially, if we close the relay, then we're going to close a contact, and 120 volt will be allowed to flow down to the DIN rail and power up different accessories. So the first one here, the K2 relay gets energized. We are going to power up our heating circuit pump. So over here, 20A1 would be the heating system pump that we're going to basically operate. So it operates when the K2 relay is closed. If I was to close the K3 relay here, it would power up another pump output down the DIN rail, this time on terminal 4, and that would be the domestic hot water tank loading pump. So when the domestic hot water tank needs heat, to heat that water in storage, then this is the pump that will be energized to do that particular function, pull the heat out of the boiler and direct it into your coil of your tank. The K4 relay here gets energized from 24 volt DC. It's going to basically close the contact. And now if we have something wired to terminal 3, which by default is a domestic hot water recirc pump, an accessory. So you can add that domestic hot water recirc function here. And now a timer program would open up for your domestic recirc pump. You can put it on timers, etc. And other control functions that are available for your recirc pump when you add it to your Viessmann control. On K5 is actually an alarm output. So it's going to basically wire to, say, like a light or maybe to a relay contact for building automation or something, for a dry contact signal for them, an audible alarm. Whatever you have that's you want to energize with 120 volt when there's alarm condition can be wired off of this terminal 7. And the K6 and K7 kind of work together here, but separately to control one device. And they're going to be connected to an adapter that gets mounted onto the DIN rail. So in this case, it's a 120 volt adapter. And then this gets connected to a mixing valve. And what we can control here basically is when we power energize the K6 relay, it closes the contact and we get 120 volt down to open that mixing valve. And if we power the K7 relay, K7 over here, it closes our contact, and now we get the mixing valve closing as far as the function goes. So this is control of a mixing valve, but that is going to come down to an adapter mounted on the DIN rail. So this adapter is an accessory. We're going to have a look at that in a moment, what it looks like. And the K10 here, if we close the K10 relay, it basically controls another pump, the 29 pump, which is considered what they call a distribution pump. So it has different functions depending on what type of kind of system or application that you're using in the application guide for that particular control. So that's how all of your relays on that particular board are going to be energized off of a 24 volt DC and the different connections that they're made. This is a similar, and all the controls we're going to talk about here today. Now, the low voltage board is connected to just to the left of that line voltage board. And it also, like I say, it has a lot of other boards connected to it. So the power supply is plugged in and it directly connects to the low voltage side right here on the top of our low voltage board. And that basically provides the power to the different sensors and relays, et cetera, that we're going to be talking about. The A8 here is a software board. As I mentioned, it is plugged directly into your control. And it essentially is what tells this particular control that it's an MW2C. So all your programming is located in here. When you do all your coding and adjustments, it's all stored in this area, but also the identity of the particular control. And when we flash up your control, when you power it up, that's actually what's happening. Just like your computer, when you turn your computer on, this is loading the software out of this board, and this is how you see it on the display screen. So it's loading that up. So if there's some issue where this board is not connected correctly, it's missing, or it's defective, you'll never, basically that screen will just stay in that loading zone. Sometimes it's a little circle that goes around. That tells you that there's something going on with the software board, and having a look in this particular area would be advisable. But when it's plugged in and doing things correctly, when you turn on the control, just like we just saw there, it's going to do its magic. On the left-hand side here, again, A10 is a lawn board, and we see the lawn board plugged in vertically on to the left of our low voltage board. And this essentially is a communication in a lot of systems. Primarily, this would be what we would use to daisy chain between each boiler. Would also have a lawn card in it, and we would daisy chain those Ethernet cables between the boilers to the cascade to set up that cascade system. There's a little bit of a different ability in the Vitodens 200s to use the 145 instead of a lawn card, but primarily in commercial, a lot of lawn cards would be installed in the cascade and also in the boiler controls, and we would use that lawn card as a communication portal between our devices here so they can all talk, as well as when we set up a gateway for building automation or for the integration of building management, we use the lawn communication card as well to plug in the RJ45 connection between the lawn communication card and the actual gateway itself. So this is our communication device to set up our commercial cascade systems. very important component. The connections that plug in on this little ribbon cable on the top here are going to be your override switch. We're going to look at that override switch a little bit later on. That's the S3 here. It's on all of the controls, different functions on all the controls. And then also the OptiLinks, so your red and your green indicators are on this side. Your plug-in connection for your interface, that's where it all gets its power and communication back to the control on this little ribbon cable on the top. And just a little bit of information here on this area down below, just because these come up sometimes with tech calls, these 143 and 146 connections are inputs. And what can happen here is you can wire connections to these cables, and you can program for specific functions. So the 143 has the ability, if we close a contact, to disable the system, meaning that we can shut it down from operating. So the control is still powered up. You'll still see everything is normal. There's no faults that happen, but nothing's going to happen. So it's until they open that contact, everything is basically being blocked. And there's different functions as far as what gets blocked when you close the contact. But just important to note, if you hadn't noticed that there's wires on the 143 connection, that means there could be potential for things like disables, et cetera, to be part of that particular system and interfere with the actual control functioning. So just important to note that if you got something on 143, it could be the reason that you're having an issue on your site. So investigate that. Same with the 146 connection or external demand. A lot of projects are basically started with this 146 just being jumpered. So the building automation system is not ready to go. The control guys aren't there to wire up that side of it. They've got the installers there. He's got everything basically done. They want to get heat on the building. So what do? They take a jumper, they put it in the 146, they program a fixed temperature. And then basically commissioning time comes, the guy sets up the system, does the commissioning, leaves the jumper in there, and then all of a sudden you start having issues with why is this control always targeting this particular temperature? It's because the jumper was left in on the 146. So I always kind of encourage people to have a look at those gray plugs, see if there's anything in there, and just make sure you know what those particular wires are connected to, why they're there. And that way there, if there's something that's kind of funny happening, you know, it could be because somebody's basically energized those connections. All right, just a little blurb there on that. But because they're part of the low voltage board here, these connections also have a DC voltage to them. So I thought it'd be interesting to kind of detail those. So if we look at these, the communication, the 145 little pink plugs here, there's two of them. Basically, they're a 28.5 volt DC connection. If you measure between 1 and 2 and measure between 3 and 4, you get 28.5 volts DC. So that's our communication between Viessmann devices on the 145. All of your sensors have about 5 volts DC coming to them basically. So basically for the resistor to function there as far as the resistance that we're going to look at. And then the digital inputs we looked at, the 143 and the 146, have 12 volts DC on there. So all these, I should mention, never apply power to these particular areas of the control because they are low voltage. They already have voltage on them. You add voltage, there's risk of basically popping a fuse here or something and causing something to not function correctly. So always dry, potential-free contacts to these. Sensor inputs, obviously there's no voltage there. The communication, we don't want any voltage on that either. And of course, never voltage on these components on the 143, 146. And now we're over to the far left. So we've made basically a travel from right to left here on the MW2C. You've got that power connection from the 156 on that 120 volt motherboard. And it plugs into our mixing valve module right here on the left-hand side. Our communication and low voltage connection at the top here, basically to power energize the 24 volt DC relays we've got here coming out of this area of the control. Our DIN rail is down here in the bottom. So basically when you're utilizing this part of our control, you've got mixing valves attached to your system. So we've got multiple temperatures happening typically in our system when this module is being utilized. Your sensor inputs here are basically anytime you have a heating circuit, basically a different temperature going out to your heating system, there will always be a sensor connected to that circuit to monitor the temperature to make sure that we've got the proper flow temperature going out to those systems. Again, 5 volt DC is what we would see there. And now taking the shroud off here, looking at the schematic, you see that line voltage comes in and it goes across the relay contacts here that are connected to the mixing valve module. Each one of those contacts are 120 volt. We'll do a specific function. The first one here we're looking at that's closed, the K1 relay. When we close that, it comes down to the number 2 on the DIN rail and is actually the heating circuit 2 pump. So whenever the 20 output here, M2, when we want that pump to operate, the K1 relay has to close to allow the 120 volt power down there to the K2 or to the number 2 relay. The K2 relay on this side here, we close that, is going to close the heating circuit 2 or M2 mixing valve. So where's that at? Down here, 52 M2. So we're floating a signal here, 120 volt, closing it. If we energize the K3 relay here, it's going to open. So up is open, down arrow is closing. The K4 relay here, when we close that, is going to energize our 20 M3. So that's the heating circuit 3 pump if we have a third temperature. And of course, the K5 relay is going to switch the mixing valve for the M3 circuit here, 52 M3 closed. And K6 is going to open the valve. So basically floating between open and close, we're going to energize in both directions. Power open, power close on the mixing valves. And those are the adapters that I had we had a look at that previously on the 120 volt motherboard when we're at a mixing valve on that as well. There is the 120 volt power adapter. So we wire from the connections here to this adapter, and then from the adapter down to our mixing valves to open and close it. We can also use a 24 volt adapter. So if we had a 24 volt actuator on our mixing valve, instead of 120, we can go directly to 24. So we power 120, the transformer here does its magic, and now we are opening and closing 24 volt to the mixing valve here instead of 120. Same function, it's just a floating power open, power closed on those as well. So that kind of looks at the different connections on the MW2C. And like I say, we're going to go back to some of those. I didn't cover all of the little boards on that control. We're going to kind of review that as we move through here as they relate to each other. But the next control we'll look at here is actually a programmable control. It's called a GW6B or a GW6C. Depends on the boiler that we are actually connecting this particular control to. It is on the 2 boilers you see in front of you here. So the first tall fella here on the left is the CA3B unit. That's our newest commercial boiler that we brought out a couple years ago. And the Cm2 boiler here, 6 different sizes of Cm2 that are available, also uses a GW6B control. The GW6C is on the CA3B control unit. To note here as well, when we go into these particular controls, they have a boiler module, as we see here, the different controls, but they'll also have a burner control module. All of the temperature safeties are connected, electronic safeties are connected directly to this little box here. So a lot of the safety functions on this control for things like fixed high limits and operating limits, adjustable high limits, are a function of this particular control here. And it feeds back that information via the 145 connection, that little pink plug we had looked at previously. You'll see it on this control too. It feeds that information back to the control. So if there's an issue with a fixed high limit tripping, it's going to be logic that's built into the burner control, which will block the boiler from firing on a high temperature and communicate that back to on the 145 plug. I'll mention that because we're going to go through a control here, the last control, which is a mechanical limits on it, which are directly connected to the actual boiler control. So a little bit of a different logic when we go from mechanical sensors to electronic sensors. Those electronic sensors are going to block the burner from firing if there's a problem there, but they're not actually part of the boiler control logic. They're being fed that information via the 145 plug. So I just wanted to mention that as we move through. It'll be clear once the presentation is kind of over it when you see the comparison between this and a mechanical limit control. The Cm2 boiler is the first one we'll look at because they are a little bit different between how the control is wired between the Cm2 and the CA3B. But the Cm2 unit, the DIN rail is not directly below it as we just saw in the MW2C. It is actually wired. The controls on the front of the unit. We use a little channel chase here. All the cables go on the chase. And now the DIN rail is actually wired at the back. So all of your field 120 volt line voltage connections are at the back. You're going to do all of your sensor connections still at the front of the control there. And we program, as I mentioned in the first slide we looked at on GW6B, we said it was a programmable control. It just depends on the application, how you're going to program that particular control. So if it's one boiler in a boiler room, you're going to use a standalone control application. And of course, we're going to program the control to look like the top one here, where basically this control looks after all the system functions as well as the boiler operational functions. If we're in a multiple boiler system, so a kind of a cascade system where we're connecting multiple units together, rather than a standalone, we're not going to use that. We're going to have one boiler we're going to designate as a lead and cascade. So it'll look like this on the screen of that particular boiler, where the other boilers are going to have what we program as lag controls. So in presentations previously, we've gone through how to set these up. If you need that review, you can go back through some of our cascade presentations that we've done in the past. When we look at the CA3, literally the same control, but it's a GW6C. The reason being is it's just essentially wired differently. So the interface is separate. It's not part of the same enclosure. So the interfaces you'll see are GW6C one, and of course the control is basically detached and it's built into the back of the boiler itself. The interface at the front here for the number 2 control, and of course we've got the actual control in the back of the unit, all the circuit boards. So that's what the control looks like. There's your lead and there's your lag. These are already pre-programmed on site for you. You have either 2 burners, you've got 2 controls, or if you've got 3 burners like we have here, 1, 2, 3, we're gonna have 3 controls. So same idea though, we've got our lead control at the top, lead cascade, and the 2 lag controls on the bottom. And of course, interfaces are right in the front. You have to take the cover off the boiler to have a look at the controls in the back. And of course, the DIN rail is at the bottom here, not in the back like it is in the CM2. So once you take the front enclosure off, you kind of have access to all that, all of the different controls and devices that are in that particular boiler. So the interfaces look like that when you stand in front of a CA3B with 3 burners. You have 3 controls. Every burner has its own boiler control. So having a look at the GW6B here, same kind of format you just looked at. So there's having the basically under the hood here, having it look at the control, pulling that little plastic cover off so we can actually see what's in the control here. You notice a little bit of a difference here on the motherboard between the MW2C and the GW6B. We got a lot more stuff going on here on this side. A lot of this stuff here looks very familiar. So basically, when we start looking at the connections as we did with the MW2C, all those interface connections, I just highlighted in this one here, a little bit more detail for you to kind of see those. We've also got the mixing valve board over here. I'm not going to take the cover off anymore. You can see where they're at. Low voltage board. We've got the line voltage board over here. And of course, we've got our override switch, our programming unit connection, and the OptiLink on this side. Our software card. Again, different software card, different control, so different software. A coding plug. So it's something different we didn't have in the MW2C, but whenever we're controlling a burner, we're going to have a coding plug connected into these commercial controls. So these are basically controlling, might be controlling the system if it's the lead and cascade, but it also is controlling the lead boiler. So it's going to have that little orange plug in there. Lawn card, power adapter, and of course our power switch and our fuse connections here that are connected on the X4 plug now down here at the bottom. We got an extra fuse now that we didn't have in the MW2C. That's the back side of it there. And of course our control here interface, which is plugged in on this little connection here on the little circuit board. And you've got the 3 different possible display units depending on how you program the control and what it looks like. The exact same format in a CA3B, just in a little bit of a different profile. So this is the lead control because it has all of the different boards on it that we just looked at. So the lead control, if we open it up, we got the mixing valve board at the top here. You got your low voltage board. We've got our line voltage connection board here. We've got our little OptiLink and our control signal and stuff still part of that. Our coding plug would be plugged into our low voltage board as well in the CA3B. Software card, line communication, power board, and our on-off switch and our fuses over on the side, and of course a display unit showing the lead cascade display on the top here for connection. Now the thing to understand is with a CA3B, the DIN rail is on the bottom, and you've got a lot of boiler here, so more than one board of control. So there's a lot of safeties that are now interlocked on the DIN rail. So that's why the DIN rail looks a little different on this unit than you see on the CM2, because now we have to control multiple burners with safety interlocks, etc. And that's why the DIN rail looks like it does here. So there is some differences here we're going to have a look at in comparison to the CM2, how it's wired to the DIN rail with relation to strictly that little motherboard, the 120 volt motherboard as we go through the motherboard as we go through it here. So here's our line voltage connection. There's our board again, just to profile it for you. I want to also mention to have a look at the 150 plug over here. It's a little blurry. I took this little picture this morning. I think it would be important for you guys to see that. We're going to see that where that little plug kind of plays into this motherboard in a moment. You'll see it actually down here, 150. So it plugs right down here in the bottom right-hand side. It is our safety connections essentially for the burner. So all of our external safeties are going to be connected to this little area here. So let's get started on this guy. A little bit more DIN rail as we look at it here. A lot more stuff happening because now we have the burner portion here to work with. So our power is going to come in on the 40 plug here again, and you can see that we're plugged in on the 20. And as that power comes in, it splits off, and now we go to two different, instead of one fuse, we have two fuses. So the switch, still one switch, but parallel connections that we go to the two fuses here down the bottom. The fuses are identical, 6.3 amp, 250 volt fuses, but basically they protect two different sides of the control here. So we'll have a look at the F2 fuse, which is essentially our burner fuse. It's going to come down here to the 151. We're going to have a look at that in a second. But let's have a look at this one here, which we've already kind of followed in detail. If you look at remember the MW2C, we power our power board here off of the X7 connection. It also comes down here, and of course it goes to two of those 156 connections. Now we have two 156 auxiliary connections here. So one of these would go to the mixing valve extension board on the left-hand side. So that's our 120 volt auxiliary power here. And of course, we've got our connections over to the relays, and those relays are the same as they were on the MW2C. So same type of control logic, same terminations, etc. When we get to this 151 plug, this is the first area where we can interrupt burner operation. And typically what you might see here would be a jumper. If the jumper has been removed, so the jumper would actually be down here on the actual DIN rail. This is kind of showing you the jumper here. It's actually kind of down here on the DIN rail. And if we were to put a gas pressure switch, low gas pressure switch, very popular item on commercial boilers, it's going to come down and basically remove the jumper and install your low gas pressure switch. Even a high gas pressure switch in series here could also be added. And if the switch opens because of a low gas condition, or if you have a high gas pressure switch, it opens because of a high gas pressure condition, that blocks the power basically going to your burner control. So right off the bat, there's going to be no power logic. If everything's good there, basically we come in on the 1 and we go right back out on the 2 connection here. So between 26 and 27 of our DIN rail, and you can see that power comes up, comes around, goes through the X4 plug on the 5 and right out back out on the 2. Powers up our connection here on our little processor. So if the power is void here, it gives us an indication of some issue with the connection to fault output, for instance. Coming down here, we go down to the 150 plug. So the first area here on the 150 plug is STB. Essentially, that's our temperature limiter. So traditionally, fixed high limit would be connected directly to this STB circuit. When we come through the 150 plug here and down to the terminals on our DIN rail, so it comes down on the 21, and goes through things like your low water cutoffs, etc. So this would be the potential freeze. There's no power here. This would be the safety side of the low water cutoff connected directly. So it acts like a jumper, which was here, and you removed to put the low water cutoff in. It acts like the jumper if there's water basically in the boiler. If we're in a low water condition, that little sensor is going to open, contact's going to open, and now we interrupt power right in this area. And of course, that's going to create a fault on the boiler control that we have an issue with basically an auxiliary safety that is open. If it's closed, then the power is allowed to come right back up through the STB. You'll see that little STB connection here, come right back up, and it splits off to L here on power, and then that branches over, and of course it powers our little U4 here. So basically, if this processor here identifies things like a fixed high limit problem or fault, you would see that show up. If we got power here though, it goes to L. L actually jumpers directly over to T1 on your 41 plug. So there's your burner plug. So power comes in on L, goes out on T1. And then if we follow T1, I changed it to purple here. I should have went maybe like green was for, the ground, so I couldn't use that for St. Patrick's Day. But anyway, we got purple. It's going to come through. It's going to come back up on the X4 connection. It's going to come down on X4-3, and it's going to come right down here and basically sit down on our DIN rail right here. So you measure power here. Basically, this burner is ready to fire. All we're waiting for is a call for heat, essentially, to get that happening. Whether that's somebody pushing a forced call for heat, like an override switch, or an actual call for heat. What we're waiting for here now is for the K1 relay, which is our call for heat, to close. So when this K1 relay closes, that 120 volt that's sitting here now gets jumped over to this particular area. And if that K1 relay closed, but the boiler was already past its operating limit, you would actually see 11 show up on your little control. So basically, say for instance, you had a set point of 60 C, but your maximum allowable boiler temperature was only 50 C. A boiler would fire up, but it would never get to 60 C because the electronic limit would basically open, and basically you get 11 on your controller saying that we've already met our set point of 50 C, maximum allowable set point. We can't go any farther. So basically 11 usually gives you some indication. You might have your maximum boiler temperature maybe lower than the set point that you're trying to achieve. So something to kind of investigate when you see 11 on your control. Not always, but something basically an indication there that you might have something out of balance there between set points and your programmable maximum boiler temperature. If that doesn't happen, of course, we get power basically coming from the K1. It energizes down on the TR here. So as long as our operating limit is not met, goes through the jumper, comes out back on the TR, and as soon as we hit power on T2 here, our burner is going to fire. So you see, once the burner goes through all of its safety capabilities and it starts to modulate, you'll see a 7 on the screen here. That boiler is in modulation and firing on your control, and everything is good to go. When that's happening, a B4 gets energized in yellow, and that's a burner hour counter. So basically, as the burner's in operation, the control is basically calculating the runtime of the boiler and accumulate over a period of time on that contact. If the burner didn't start, or there's some sort of fault that happened, so if, say for instance you got an F2 fault, let's turn that down. You would actually instead of the counter being energized, the S3 connection on that 41 plug would be energized, and that would basically indicate a fault. So now the red light would show up on your little OptiLink telling you you've got a problem with your particular system. So there's your different connections as we go through there. The motherboard, basically on the CA3B control, there are some auxiliary safeties that are, because of the commonality of the boilers and the burners on this, there are some common safeties that have to basically be interlocked, and they are mechanical switches. So I kind of mentioned that these boilers are operated off of electronic limits, etc. there are some mechanical safeties on the CA3B to be aware of that will basically kill power to the control completely. And they're identified up here, K and L. So this is the X4 DIN rail, where all your safeties, low water cutoffs are connected. You see your jumpers here for different, remove the jumper for another safety. And then there's these safeties that are already pre-installed from the factory. So low water cutoff would be a connection here. We'd open that up. So that's part of the 150 safety circuit we just looked at. But we've got a vent temperature switch, which is basically down here on your boiler. So at the back, right where the vent is, you've got basically a switch here that opens at about 110 C. A little reset button is right there. You have to take the little plastic cover off and basically push the switch, and it'll basically reset that. And then we also have L here, which is a fixed high limit switch. Again, that's set for 100 C. 210 Fahrenheit. Again, back off a little cover here, a little flathead screwdriver. You unscrew that, and you can flick the little switch in here to reset that control as well. So those are not on the GW6B. They're not on the Cm2 boilers. They are specific to the CA3B, but they can also interrupt power to that motherboard and basically kill power altogether to your control. So you walk into a CA3B and there's no power on the display. First thing you might want to check, or just to see if these switches are basically open, and basically reset them. So something different on the Cm2 and CA3B there, just a detail. On the MW2C, basically we just looked at the GW6B, essentially the same, but the MW2C doesn't control a burner, so it didn't have that coating plug. Now we're controlling burners. We're going to have that little coating plug, so that little A9, which is plugged directly into your control here. And the coating plug is in every control that controls a burner, with the exception of our wall mount little Viessmann 100. 200 has a coating plug. The CU3A has a coating plug. All these boilers that we're talking about here have coating plugs, and they identify the actual size of the burner, things like maximum temperatures. All those things are part of that. Turn down ratios and modulation are all part of that little coating plug. It's a little microprocessor chip that you're plugging in basically. And just some identification here. A couple of things to note. You just can't take a board out of one boiler and throw it in another boiler with a different coating plug on it. It's not going to accept that coating plug that has a different burner, et cetera, connected to it. So you would get a B7 fault if that was the case. So these are specific boards for specific size boilers, and those coating plugs are keyed specifically. So sometimes they won't even fit in that little area. You can't plug them in, can't make the connection because they're the wrong card for that particular board. So important little detail there, what those little things are doing, their function. And of course, in some processes, part of the replacing of controls and motherboards and stuff, you may have to unplug and replug that coating plug back into the new control.
Can I just point something out, Scott?
Sure.
Those coating cards, if you're going to start replacing a coating card, let's say, you might have to reset in software the pairing between the two, because once the motherboard and the coating card see each other, they kind of make a relationship and says, "You're my buddy."
Yes.
If you put a different coating card, even if it's from, let's say you took one out of one GWC control in the CA3B and put it in another one, it might still give you that fault because it's not the motherboard that it saw before. You have a procedure. If you had a replacement coating card, there'll be a procedure that you have to reset some some settings in coding.
A better way of saying it than I was trying to spit out there, but exactly. So there is that. There is a little bit of a function there when you plug that in, that little process. I think it's address, is it 92? I think in coding 2 that looks after that particular connection. Yeah. I think it is. Yeah, I might be wrong. Anyway, that's something to kind of consider what that's doing and its function. Again, the voltage is down here on the low voltage board. And the mixing valve board on the GW6C or GW6B is exactly the same as the MW2C, but it's wired differently. So you see the connections, a 40 connection here where the 156 plug plugs into it from your 120 volt printed circuit board. But now when we wire to the DIN rail, we wire directly to the DIN rail here. So now there's actually direct connections for 120 volt floating mixing valves. So again, your relays here, same functions. Now we got the different pump outputs. You see the relays that control those, and the outputs now for the mixing valve opening and closing are directly connected. So now you can wire your mixing valve directly to the 120 volt without having an extra adapter. We still have the ability of, if we want to operate a 24 volt mixing valve, you would have to add an adapter in that case to the DIN rail, and now take the power off of the 120 volt floating here, again, to the 24 volt adapter, and it's going to basically use a transformer here to bring that down to a 24 volt to operate a low voltage actuator. Your sensors here for M2 and M3, still 5 volt DC, so a lot of that stuff is still the same. So just a bit of a difference there, same control, different way of wiring, same idea. Now moving to the final two controls, I bought these kind of in the same, because usually you're going to see these in the same boiler rooms. Not often you would see the MW1B without a GC1B attached to it. You may see a GC1B on its own in a boiler room, not connected to a cascade, because they are standalone controls as well, the GC1Bs. But a lot of times in cascades, you'll have these two in tandem. So the cascades, the NW1B, the GC1B would be on the boiler. So that's the GC1B sitting right there. You see the DIN rail directly below it. MW2C is very similar, with the exception of the interface here, to the MW1B and MW2C are very similar, with the exception of the interface here. And you're going to see that as we move through. So the first thing we'll tackle is the cascade. And these are existing boilers right now, the Veteran VD2 and VD2A boilers for new installs. There also could be retrofits to older VD2 systems, VD2A systems, where the control needs to be replaced, as well as Vitacrossal 300 CT3. So we don't make the CT3 Vitacrossal 300 anymore. It's been replaced with the Cm2 and the CA3B. But as far as retrofits, these controls would be able to retrofit in a cascade or standalone system to those boilers as well. So there's the wiring schematic, very similar again to the MW2C. As a matter of fact, all these boards are pretty much the same. The mixing valve board, we've got on the left-hand side, we've got our low voltage, our line voltage boards here. Our interface, a bit different. Kind of not touchscreen. Now we've got the navigation keys here and our OptiLink, and of course the connection in the back here for the interface here to connect into the unit. Our software card, our LAN connection here, our power supply, and of course our on-off switch, and only one fuse again, just like the MW2C. And everything here is the same, basically, as the MW2C we just looked at. So there's no difference between how the power moves through this control as it did on the MW2C. On the low voltage control board, again, you got your voltages down here. No coding plug, right? There's no burner operation on an MW1B. It doesn't control a burner. That's left up to the GC1B, as we're going to look at here in a second. So nothing here, basically, to review. And we're back to if we have mixing valves on our mixing valve extension kit on the NW1B, we add the adapters for 120 or 24 volt, and we can allow those things to operate as we see there. So essentially, if you're looking at the NW2C and MW1B, you've got pretty much identical as far as how the power moves through it and the different boards. The GC1B is a bit of a different beast, probably the busiest of all the boards. That's why I saved the best for the last here. But again, you've got this on the boiler itself. So usually on the side, not in the front of the boiler, you're going to see these attached to with the DIN rail down below. And now you've got a burner you're operating here. Basically a Weishaupt or yellow burner, typical on these particular units. So that means the voltages for the motor here, fan motor, would be different: single phase, 3-phase, 230, 575, whatever you're working with. And they will basically have different wiring schematics for that power to come off of that for that particular motor. The display is a little bit different on this control, so I thought it'd be interesting for you to see that. So in standalone, you would look something like this on the GDC1B. You have domestic capabilities with a domestic sensor, of course, space heating for one temperature. If you have this connected to a cascade, of course, the cascade looks after all those functions. You won't see those, but you see boiler temperature, where pumps are on, and whether or not the burner is in firing mode, regardless of if it's standalone or cascade. So just a bit of a different look to that. Opening up the control, and this guy flipping the lid, you'll notice that there are now capillaries with little capillary bulbs on them. So now we're back to some mechanical temperature limits directly connected to the boiler control. Not electronic limits, but basically mechanical limits here, basically know one temperature, whatever they're set at. So not feeding back temperature to the control, they'll just open when we hit a temperature that the control is essentially programmed for. And those are directly connected to that power module we'll look at here in a second. So taking the cover off this control, you notice there's no mixing valve module. This GC1B will not control any mixing valve. So it's one temperature for heating on a standalone application, or it's basically connected to a cascade that does all that stuff for it. So the GC1B control, no mixing valve module here. So we start off with a low voltage control board here. Got the coding plug in there now. Remember, we're controlling a burner. We've got the line voltage control board here, moving the power switch away here. You can see the control with again with the burner connections on the right-hand side. Our OptiLinks, as we have before, our software cards, coding plugs, communication cards, power adapter, and of course, this is a real jazzed out power connection now. You've got your two mechanical limits, your fixed element, your operating limit. You got two fuses. You got this extra little switch here, which is kind of cool. We're going to talk about that as well. And on the back here, you'll see the mechanical limits now. So there's your fixed high limit. There's your operating. Oh, sorry, that's your operating or your fixed limit down the bottom. And this is your operating limit at the top here. I think this is flipped upside down. This particular when I took this picture, and those are where those capillaries are connected to. So the capillaries are directly connected to these little mechanical switches that are connected to this board directly. So those little capillaries are going to end up somewhere in a sensor in the boiler to pick up the temperature of the boiler itself. So here we see the 120 volt motherboard on this unit, and lots of stuff to have a look at here on this control. So we've already got the neutrals already configured and the grounds. The power comes in the 11, and now we're going to go up to basically the little branch here, and we're going to split between the burner and the pumps and our power. So all this stuff is the same as we just looked at. Powers the module down, powers up our relays down to our two 156 connections, and that basically completes a circuit that's fuse protected with F1. F2 is our burner again. So it comes over through the switch, power the switch on through the fuse, down to our 151 connection, which goes to 20 and then comes back on 19 on our DIN rail down here. So what does that do? That is going to basically, if you have this, usually it's jumpered. So we'd have a little jumper down here. If the jumper is removed and you got a little contact down here, it could be a boiler door kill switch. So if you're opening up the boiler to do service here, there would be an accessory that you can add that would basically kill power to the 151 connection here, break the connection when that door is open so that we don't have that burner firing when you're in there doing your work. That would be bad. So that would be an accessory that you can add in there for that function. If there's a jumper in there or everything's good to go, the power just comes back up on 19. And now we move up through F6. And F6 is our fixed high limit. So that little green dot in the middle here is actually a reset button. So if we have basically a fixed high limit fault, we push that to basically reset it. And you'll see the back of the fixed high limit, you've got your connects here for checking for continuity, for power across the fixed high limit. And you'll see it's set for, in this case, 110 C, so about 230 Fahrenheit is the fixed high limit temperature on this particular unit. If it opens here, of course, you're going to get a fault indicated that you need to basically reset that unit there. If the fixed high limit's good, we closed, the wire comes down here. So there's our fault for the limit, comes down through. It goes down to our 150 plug. So down to 12 on the DIN rail. So we look at 12, there it is. And what's connected to 12 is the low water cutoff, your chain, your safety chain, pressure switches, external temperature limits that you might have out there in the system that might be required by your inspectors, whatever it could be, basically all put in series on this particular chain. So it comes back from 12, it comes back up on 15. So if we basically have a safety that opens, we have no power up to 15. And of course, that's going to create a fault to the unit. So we're going to have a problem. If we basically have continuity here, power's going to come back up on that 15, and then it goes, it's branching off, goes to a little processor here saying that all is good, and then over to the L. And then of course it jumps over to T1, and T1 now does the same thing as it did in the GW6C, only now you've got a mechanical limit up here that we didn't have previously, and we got to switch. So the first thing we look at is the operating limit. So there it is. So basically this is just like a standard aquastat. You turn this, and if we have this set too low and our set point is higher than this little operating limit, we'll never reach that set point. This is going to open at whatever temperature you see on the scale here. So if you need a higher temperature, you take the little cover off, which I've done here, and you start breaking the little teeth that are surrounding that little dial. So now you can turn this dial to a higher position. So the idea there is basically we only set it to where we actually need it. So that the idea is to keep the temperature as low as possible without having, overheating is basically loss of efficiency, but we still need to get the temperature we need to get to. So we set that to our absolute required maximum temperature and make sure it's higher than our boiler operating electronic limit, as well as the set points that we're going to try to achieve for this unit. Otherwise, we'll never reach them because this will keep opening when we're trying to reach them. So if it's closed, then the power comes back down, and we end up down here on that power burner on, waiting for the K1 switch here to close for the call for heat, which brings us to the next component right here, S2, our TUV switch. So this switch here, you'll notice is if you ever tried it, it's basically spring activated, which means if you don't hold it down, it's going to go right back to its reset position. So you have to push down on the TUV here, and you hold that down, and what it does actually, because it's parallel to the adjustable limit, you're actually bypassing the adjustable high limit here. And when you bypass the adjustable high limit, now we get that power coming down, bypassing our limit, going right up to T2 on 16, and our burner is going to fire when I hold this TUV switch down, and it's going to fire until I trip my fixed high limit. So this is a test switch for fixed high limit safety testing, and it must be held down to trip the fixed high limit. Otherwise, it won't do what we need it to do. So removing that out of the way, it's basically the power has to come through the K1 relay or call for heat. So when it activates, the power basically comes back down on 17. We come back up on 16. And basically we have our burner power on right now. So the burner basically is energized. We've got our hour counter here, just like on the GW6B and C. Something different that you saw in the other control but wasn't utilized, and this control it is when we're actually modulating this burner, the 90 plug here is being used. So it was part of the GW6B control, but there was no connection to it because it wasn't used. The burner control actually looked after modulation on the GW6B and C, where this control actually looks after that modulation. 120 volt floating, and basically between T6 and T8, and we see the position is right now, we are going to be ramping up the modulation. So the burner is going to be ramping up, driving up to a higher fire position. If we had basically a T6 to T7, so basically if K8 here switched to T7, then we'd be driving down to low fire. If we want a hold position, K9 opens and basically holds the modulation wherever that might be. So that's essentially how that 90 plug works. So we actually drive the burner to high fire and drive it down to low fire using a 120 volt floating circuit on these K8, K9s. Very easy to test here as long as you know what you're testing at that particular point. If we get a fault, the burner couldn't light for some reason, and it basically comes back that it didn't light off, it's going to trip our little processor here, give power to it, and we're going to get a burner fault on our control telling us that we've got a problem that needs to be addressed at the burner specifically. So B4 and S3 basically alternate. So if B4 is on, we got our burner running. If S3 is basically on here, we've got a burner fault and we're locked out. So the low voltage motherboard on here is same same type of setup as we had in all the controls that we dealt with. We're going to have a little look here, though, at this little emission test switch, because it kind of comes into play on all the controls we looked at here. I thought I would save that for the end. Little switch here, and what that little switch will do for you on the GC1B and the GW6B and C, it can be used as an override switch. Or emission test switch, I should say. So we flick the switch from its default position down to the hand, and when we do that, it manually energizes our relays here connected to the motherboard. With the exception of a couple, your low volt, any mixing valve ones will actually close, so we don't basically overheat those particular systems. But your pumps will be energized here. The burner will come on. And we would use this typically as a function to test the adjustable high limit. So the TUV switch we saw here on the GC1B was a fixed high limit. We can use this emission test switch to test the adjustable high limit to make sure we shut off at that safe temperature. So both GW6B, C, and the GDC1B will use that for that function. When we use the override switch on an MW2C or MW1B, it's not going to fire a burner, but it'll do the same thing. It'll energize the relays here connected to the motherboard, and our pumps will run. That means that we can dump heat whenever the boilers are basically turned on and we're doing some testing, etc. We override switch the cascade, and now we can dump that heat into a domestic tank or out into the system somewhere. Obviously, considerations of safety would be primary as well there. So that's what that little S3 switch will do. It basically manually energizes relays, and will start a burner to test the limits. So just a quick review here of these controls, just to kind of wind it up. That was the information I had for you today. And we see the different controls here. So the cascades are on the top, our basic cascade and burner control here, and of course our burner control G71B on the bottom left here. So MW1B, MW2C, no coating plug, no controller burners. The boards, very similar functions though between all these units. GW6B and C controls are programmable devices for standalone or cascade, lead, or lag control operation. They all have coating plugs in them because they all operate burners as well. Electronic limits, with the exception of a couple of common mechanical safeties on the CA3B, but the burner controls on the CA3B and the CM2 really look after those temperature limits and communicate faults to the boiler control if there's an issue with one being exceeded. And the DIN rail is not directly mounted to the control. So it's either going to be part of the enclosure on the front of the boiler like a CA3B, or that's mounted in the back of the boiler while the control is mounted on the front. And the GC1B, you have the mechanical limits, specifically on the for fixed high limit and operating limit. You don't see on the other controls electronic limits, and no mixing valve extension board available for GC1Bs, and of course coating plugs because they're going to operate burners in their system. So I hope that you found that information useful. Like I say, I think having this archived and just using it as a complement to what we have available in the manuals, and that's strictly what this is all about, is the manuals are the source, and this is just a complement to what we have available out there for you to review. And as in due time, after Mark finishes up his 12-pack of green beer, he'll get this thing up on our YouTube channel ready for review. So thank you so much. I'm not sure, Mark, do we have any questions?
I have one. Am I limited to the 12?
Absolutely not.
Okay.
You have the authority to
I just wanted
as
to
long as you can find enough green dye, you can have as many green beers as you like.
All right, that's good. That's the only question I had. But we did have one. We did have one came in from one of the guys, and it was related to faults that show up for limit opens and limit faults. If there are any faults that happen, say in a lower cutoff or temperature sensor or an e-stop or something like that that's tied into the safety chain, there will be a fault code comes up on the control. If it's a fault that's directly connected to the burner, like a combustion fault, or in the GW6 B or Cm2 or Ca3B, you'll also see that fault on the burner control. It might be a different number, but it'll be a related fault, and the manuals will tell you that. You don't ever have to get onto the circuit board to create a fault. Like Scott said, there are override switches to bypass settings so you can get to those safety checks that some of the inspectors want to see.
Yes.
And if it's boilers without a mechanical high limit, you're not actually tripping a mechanical limit, but there are methods in the service manual for you to do it to meet all of the government regulated tests. The tests that we have to meet are under a code called CSD1. And they are specific tests for, if the government inspector wants to see it, he'll be following those regulations, and those procedures are in the service manual if you need to do a test for an inspector, or if you just want to do it just to see.
Yes.
With the electronic redundant sensors, doing the physical tests isn't quite as important. When you have the mechanical limits, the only way you can test it is actually make it trip. But when we use the electronic sensors, because we're using two sensors that are being compared to each other all the time, if they drift apart from each other, the control knows there's a fault. So you really don't have to test it because it's always being tested all the time.
Good point, right? It's good. As that boiler is firing or as the temperature is being monitored, if there's some sort of issue there where, a mechanical limit, you may never know. It might just be, the gas is let out of the bulb or something like that for some reason, and it never actually works until it, you don't really notice that until it actually becomes a problem. So your operating limit may actually never, may actually not be faulting, or may not actually work, but as far as open. But if your electronic boiler sensor is down to a lower temperature, it may never reach that point anyway. So it's, like I say, with electronic limits, they're always being monitored. If there's a problem, it's picked up right away. Whereas, as Mark said, mechanical limits, you really have to test them to basically make sure that they are going to open when they're supposed to open.
Yeah, and going forward, you're going to see mechanical limits disappear from controls like these, because we don't really want to drive the boilers to these temperatures to do the test. We want them to be safe. And if we use two sensors that are always compared to each other in the same spot, so like the 3A, 3B or boiler sensor, or 15A, 15B and a flue gas sensor, if they're not measuring the same temperature within the tolerances of the sensor, that generates a fault. So if it's not reading the right temperature, it's going to generate a fault. And if it is reading the right temperature and it gets to that temperature, the boiler is going to trip it open anyways. So it's, again, going forward, the mechanical limits are going to disappear from all of our products. The only boilers we still have it on now are the cast iron boilers, because they were designed with mechanical limits.
Right. Good point. Yeah, everything I say, as new generation of boilers come out, that's what I've noticed is, even on the smaller boilers now, your little mechanical fixed high limits have now been replaced with sensors instead of that. So it's going right back to not just commercial, but right into the residential realm of the world.
Where products we're releasing this year will have no mechanical limits in them. They'll all be electronics with redundant backups.
Welcome to the great new world.
That's right. You can check your limit with an ohm meter now, because you just check the sensor if it reads bad.
Exactly, right. So just a different way of doing it. So but same kind of stuff. There'll still be procedures for testing things. It'll just be a slightly different procedure from what you're used to.
Yeah. That's all the questions we had. Just that one. You did a really good job. So you explained it so well. Nobody had any questions. All
right, excellent. That's what I like to hear. You're always in my corner, Mark, so I appreciate that.
I try to be.
Thanks so much.
As
much you can.
And I try not to drink the green beer until after we're done.
There you go. So I mean, like I say, I hope a few of you out there enjoyed a green beer while you took this in. It's appropriate for St. Patrick's Day. And like I say, you'll probably drink a lot more now. It's frowned upon.
It's frowned upon. HR rule or something.
Yeah. You should check his pockets for green dye today.
That's right. Yeah. Harold's German. He wouldn't be doing green beer.
There you go.
Okay. Well,
taint our beer with that green dye. All right.
The silliness. So, not that silliness is bad. It's
Thank
just
you
for overtime. So.
Yeah. we're at the end here. So
Yeah.
we have another one coming up. I think this is going to be repeated in a couple weeks. So if you know anybody that you think might be interested in it, let them know. They can sign up for it for the round two. Round two is always better than round one. We just do an improved way of doing it. So we always give our best shot at number two. And I think we've got some other presentations. I think even tomorrow, I think there's a CA3B presentation.
Peter Crossell, CA3B tomorrow. And there is on the 23rd, we have maximizing condensing boiler efficiency. That'll be a good one.
That is an excellent one.
We're not doing that one, so that's why it's going to be really good, right?
It's going to be really good. Yeah.
and we have the CA3B again repeating on the 25th. And Scott doing this one over again on the 31st. So there's lots of coming up. There's also one on April 1st on troubleshooting FB faults on the CA3B. This is a fault that has several different directions it could be coming from. So we'll kind of walk through all the different variations of that so we can identify what direction to shoot from.
That's another good one. The fault ones are always good.
Yeah.
Really good ones to have out there. So looking forward to that one and taking it in. So we got you commercial guys covered. This month of March seems to be the commercial month. Like I say, look forward to
Miranda's working on the schedule now. We'll have more coming in because I think our schedule runs out April 1st, but there'll be more after that.
Yeah, Moretta's busy getting together the topics and the dates and stuff like that. So I had a chat with her a couple days ago. I think she's got some dates in mind there. She's going to throw passes there. So look for those upcoming presentations in April as well. So
yeah, and if you don't,
we'll look
email blasts. You can always go to the Viessmann websites, both the USA and Canada websites under the Academy, and look for upcoming webinars, and you can register right on site there.
Yep. And just one more plug before I say bye. If you don't have the Viessmann Orange app, that is basically will get you basically all this information plus a lot more things about documents and other things that Viessmann are up to. So if you don't have that, that is an excellent little attachment to add to your tablet or your phone or whatever to keep up and current with what Viessmann's doing, what we're up to, kind of trouble Mark and I are trying to get into, here on a weekly basis.
Great.
So that's it for me.
For me too. So thanks guys for showing up.
Yeah, absolutely. Thank you so much, and look forward to seeing you. Not seeing you all, but meeting you all here again virtually in the near future. Take care.
Right.
Bye now.